Joining in. This is the blockchain revision hackathon. The people who have joined recently, I just explain the format of the same. Thank you, Suju ma'am, Vasu sir, Sharayu, and I request user. Maybe you can rename yourself. I'll not be able to pronounce know your name, right? Thank you so much, everyone, for joining in. So, people who are joining us from our social channels, I request you to join us from the Zoom link that is shared over email. Great. Thanks, everyone. So let's begin. So to explain the format, let me share my screen. So all these revision hackathons are going to be a repetition of the actual lectures done by the primary faculty here, Professor Pandurangan sir. So let me share my screen. Let me know if my screen is visible. Here. Great. So if on your Teachable account, you'll be able to see that. Let me know if my audio is clear. If my audio is clear, type A in the chat box. Great. Thank you so much. So if at all you open your Teachable account, you'll be able to see that we have revised all of our previous lectures, and in our previous hackathon, we have also revised most of the module 4. We've understood how the transaction happened, but because many people, thank you, Sharai. So many people, how many of you have joined recently in the past month itself, right? So if you've joined recently in the past month, type me in the chat box. Yes, people who are watching us on our social channels, you can chat, use the chat option. Great. Thanks, Sushant. Thanks, Vijay Lakshmi ma'am. Great. So we have a few people who have joined recently also. So now you can see that the actual lectures, if at all you go ahead and start any of the lecture, you'll be able to see that, we are going to do a repetition of the same, right? So the name, all of the, all the topics, including the labs. And I would request you to take the quiz while you are doing the hackathons itself, right? So if you're already going through the actual lecture by Professor Pandurangan, that is also fine. If at all you wish to go through the sessions that are happening currently in the revision, that is also fine. Great. So now today we are going to cover more of what we covered in our previous session, which was on to the wallet and details of the wallet transaction. But before that, because we have a lot of people who are new, I'm also going to go a little back and come back on so that we can understand it better, right? So even people who have attended previously missed any sessions also will be able to go through that, right? So let me share my screen and let's begin. Great. So if we go a little back, we'll be able to understand that first we understood the issues with the currency. We started by understanding the issues with the currency. After that, we have gone through the decentralized systems, right? So yeah, my screen is not yet shared. Great. Yeah. So now you can see that. So first we have gone through the currency issues. We're going to quickly glance through the previous chapters, and then we'll resume what we were continuing in our previous session. If there's any doubt or anything that you want to add, go ahead and put that in the chat, right? So we have gone from the issues of the currency, how a system was required, which was more of bit based or some cryptographic based, and that is where the need for decentralized systems came in. We have discussed about that. We've understood that having a centrally controlled currency is it also is going to lead to a lot of single point failures as well. So we've discussed all of that. And then we have gone into understanding what are decentralized systems and how these decentralized systems, what are the pillars of it. So we also understood Is yes, there's any question, can let me know. Yeah. Okay. So you can mute if there's nothing. Okay, great, thanks. So we've understood. Yeah, so people who have joined just recently, do not worry. You can go through these revision hackathons are going to be a repetition of the lecture by the primary faculty, Professor Pandurangan. You can go through the actual lectures. The recordings of the revision hackathons will be available in your inner circle, right? So you need not have to, complete. If you are joining recently, it would be like you're parachuting into this. Do not worry, you can go through all the sessions back again. These revision hackathons happen in a cycle, right? So once we end all the modules, and we're going to begin from the first, right? Great. Okay. So we have a question in, yeah. User says, transaction verification algorithm forms. Yeah, so we'll also be covering that, sir. Right? Is there any specific questions that you have? Yes, referring professor's slides. Yes, correct. If there's any specific question, you can let me know, sir. So it will be helpful. Great. So we, in the decentralized systems, we have understood, the basics, the pillars, which we'll also be discussing as we proceed forward. One, we'll be discussing as we go forward the consensus protocol. Then we'll also be discussing about the distributed ledger technology. We have discussed how this ledger, which is common, which is going to hold all the transactions, is distributed and is transparent and available for everyone on the block, right? So in our previous lecture, we also were able to access one of the block 5 lakh, where we were able to see a few details as well, right? So we'll also be discussing as we proceed forward more about smart contracts. Smart contracts are a way to execute code that is going to automate any manual work that could happen on the blockchain network. For example, if at all we want to automate any particular system, like let's just say if we are taking an insurance use case, a smart contract can check if there is if the person is eligible, if he's eligible, and then it will automatically go ahead and allocate that particular claim to him, right? So this is all automation that can happen. We'll also be discussing about smart contracts, a little more about solidity and more about coding also as we proceed forward, right? So we've understood the numbering systems. We've seen at length on how to convert from one base to others. So we're not going to go in detail about that. But I would say that you can definitely go ahead and follow the lecture by Professor Pandurangan or the revision hackathon, where we converted from one system to other. Like we converted from decimal to octal, from octal to binary. So there were also a few tools that are added in the resources section, where you can go ahead and instead of trying to do it manually, you can use these tools to convert from any decimal system to octal or binary. Right. So then we got into the understanding of hashing, how we are going to compress a larger, text or a bit string in and compress it into a smaller format and a more secure format. So that is where we understood more details about hashing, where any input that is coming in is broken down into chunks, compressed using the algorithm, and the output, whatever is getting generated, is going to be unique. And it is some, if at all there are a few properties to whatever output that gets generated. We also discussed about these properties. So whatever output that comes out of the hashing function, it will have a property such as collision resistance, which means it is difficult to find two inputs with the same output, right? Meaning that no two outputs will be same, right? So we also understood that even a smaller change in the input is going to produce a very large change in the output, right? So we also have understood that particular property. And there is another property which is pre-image resistance. Professor Pandurangan also mentions it briefly during his lectures. The pre-image resistance is where it is difficult to access difficult to determine the input given the output. So if somebody gives you an output, an output of the hash, will not be able to easily determine. It is going to be uh, very difficult to generate the input based upon the output, right? So that is all something we have also discussed, right? So then we came across the SHA-256, where in SHA-256 we also used the online link to generate hash of various text inputs. You also, if you have attempted the quiz, you'll be able to attempt it based upon the tool that is given, right? So in the quiz, you can see that you are being asked a hash of a particular string. So you can go ahead, use that tool to generate the hash and answer the quiz, right? So all of this also has been covered in our previous hackathons, right? So let's go forward and see what we have covered post that. Great. So once we have understood hashing and all the other important aspects of it, then we went into the public key cryptography, right? So let me share my screen. Yeah. Screen is visible. Yeah. Great. So then we've understood why there was a need for public key cryptography. We've understood here the difference between the private key and the public key. In private key, it is more of a symmetric key cryptography, which means whatever key is used at the time of encryption is also used at the time of decryption. If at all there is some person who is able to eavesdrop or understand or come to know about the private key, he'll be able to decrypt the message, right? So this is a private key. So then we understood the need for public key. In public key, what happens is you're going to have a public key and also a secret along with you, right? So there are two keys that you will have to actually to be able to decrypt the message, right? So in public key cryptography, the public key, whatever is there, is used to encrypt a message, and then that message is sent to the person to whom you want to send the message, and that particular person will be able to decrypt that with his own private or secret key, right? So we've also seen an example of the same, right? So this public key cryptography is used in many of the cryptographic algorithms, right? So let's understand this with the example. So we have seen that if B is trying to send a message to M, so first there'll be an encryption that is happening at B's end. What he will be doing is he'll be giving his message along with the public key of A. Then he'll be generating a cipher C, and that C is going to be used while decrypting by A. The person who's received the message, he'll use C along with his own secret key, and then he'll be able to get the message back, right? So to be able to access or decrypt the message, you would require to have your own secret key, and we also understood that this secret key has to be only be available with you. It is similar to your own wallet password or something which only you have to have knowledge about, right? So we have understood about this as well, right? So after that, we also understood signatures, signing, and the decryption of the same as well, right? So if you see in this one particular example, expanding on the previous one, if B is trying to send a message to A, even if there is an eavesdropper who's trying to understand or tap wire the message, he will get C, but he'll not be able to decrypt the message because he does not have knowledge about the private key or the secret key of A, right? So first what B does is B runs the encryption algorithm with parameters, the public key of A with the message to generate C, and then send C to A, right? So C will be able to decrypt it by using his or her own secret key. So we've also understood this particular aspect of the public key cryptography. Then we've understood more properties about the same, right? So then we proceeded forward to go into understanding more about digital signatures, right? So what are digital signatures? Digital signatures are something similar that we have understood in the decryption and the encryption portion of the cryptography. Similarly, whenever if you want to authenticate or sign any agreement, because we are going to work with a lot of contracts and agreements, digital signature is something that becomes very essential. And this digital signature is also part of your Bitcoin wallet and Bitcoin ecosystem as well. So knowledge about digital signature is very important, right? So if at all, when you're signing a contract, or automatically when a contract is getting executed, any agreement, digital agreement over the blockchain network, you would have to digital sign it. And how does that the process happen is this way. So the public and the secret key are used for signing process, as we have seen previously. Now, digital signature serves as a binding association similar to physical signing of a document. So the key properties of the signed document are these two key properties, which you can also see will be in your quiz and all. So having knowledge about it is very important. So it has two properties. We'll also understand the two properties here. One is the unforgeability. Any digital signature will not be forgeable, because it would require the access to the secret key of that person. Without that, it is not possible to forge or duplicate. And even the signing algorithm, it makes it very difficult, because every time whenever you execute the signing algorithm, random hashing happens, and you'll be only able to verify that signature that is getting generated with the secret key of that particular person, right? So you'll be able to only match it because the public key matches the secret key, right? So the other property is non-repudiation, which is, for example, if the sign is not forgeable, there is also the property that is required to protect both parties, who is signing and who is receiving. The other person should not be he should not be able to deny that he ever took that particular agreement, right? So this both properties are true in digital signatures. And we also understood here how this works. So what happens is, in the signing algorithm, the message along with the secret key are used to generate sigma. Now sigma is the signature here. And whenever somebody wants to verify if this particular agreement or message is properly signed by the same person, or who's the person who signed, or if the document is authentic, then he's going to use the verification algorithm with input as the signature along with the agreement and the public key of the person. He would not, when you're verifying, you would not require the knowledge of the secret key of the person. You'd only require the public key of that particular person. If it was properly signed by the same person, then the verification algorithm is going to say, yes, it is verified and it is an authentic signature or authentic agreement that is being agreed upon, right? If it is not, is going to say no. So now one of the properties, anybody can verify a particular signature matching the agreement, but only the person who has the secret key will only be able to sign it, right? So these properties also we have understood. Another thing that we need to understand here is, while we are trying to sign, there could be the agreement could be larger in size, and that is the reason we do not directly sign the algorithm, the agreement. What we do is we sign using the hash of that particular agreement, right? So instead of directly giving the message, we are going to use the hash of that particular message. So what the hashing function, which we have discussed in our previous slides, does is it is going to compress it and give a fixed length 256-bit output, right? So the signing algorithm will always expect this 256-bit output. So it is very much predictable and it is going to process flawlessly. Right, so we also understood if at all you want to go at length and in detail, you can always go through the lecture as well, or even the previous revision hackathon. Right. So here post that we have understood one property of the digital signatures, like what happens while somebody is verifying or signing, right? So if somebody is verifying if the verification algorithm is taking the signature, the agreement and the public key and is able to verify yes or no, how is it able to do? So what is the background logic behind this particular algorithm? So then that is where the elliptic curve cryptography comes into picture. We've also discussed it, but in a brief manner, I'll try to explain it here. So what happens is when this verification is happening, the point, so because we have the access to the public key, the algorithm itself uses one point, which is called as generator point. And using that, it will check if the secret key is also there on that particular curve. So that is when it will understand, okay, this is a verified algorithm. So though it is not getting the input as the secret key of A, because the algorithm has a functionality within itself, the logic of the algorithm is going to use the elliptic curve cryptography, which we have discussed in our previous sessions. So it will automatically use the generator point to match it with the signature on the curve and then going to say yes or no, right? So that also we have discussed in detail. So, not going to discuss heavily in detail about the curve, but what this digital signature is going to use this elliptic curve as the points on the elliptic curve are going to be the points, the public key and the secret key and the generator point. So this is the logic that is behind, this is the curve that is behind the digital signature or the public key cryptography, especially the one that we are using in the Bitcoin, right? So we have understood this also at length. The equation for the curve here is y square equal to x cube plus 7 mod p, right? So this is what we have covered regarding the public key cryptography in our previous hackathons, right? So I hope, okay, Vasu sir asks, yeah, so Vasu sir, these presentations are also loaded. So if at all you can go through your inner circle, you can find them. If you require any other resource that you find it's not available, you can always reach us out, or you can bring it up in the hackathon itself, no problem. Which is the third party mentioned in point 2? Okay, so you're talking about this particular slide, sir? Are we talking about the digital signature slide? Yes. So here we're not talking about any third party. Basically, the logic of digital signature uses the elliptic curve, right? So that is the inner working of the signing and verification. So that is a property and part of the digital signature only, sir. So it is not a third party. So that digital signature is working on this special curve, which is a very unique, which has a very unique property. So this is called the elliptic curve. And in this curve, there are a few properties, right? So every line or curve has its own equation. So the equation for this particular elliptic curve is y square equal to x cube plus 7. And it is symmetric about the x-axis. So what happens is it has a few properties where if you have one point on the curve, you will be able to generate new point on the curve. So there are some trillions of points that are available on this curve, and hence there are so many Bitcoin addresses that could be generated. There are so many signatures that can be generated, because even Professor Pandurangan sir explains the whole population itself is 7 billion, each person having as many as addresses or signing required also. This curve is going to satisfy all of that particular points, right? So every we also discuss how the wallet address and how this digital signature use the elliptic curve as a property. So this is discussed in detail also, sir. I'll point you out. This is in the module 3 of the teachable in the course, right? So we've also understood how to know if a point is there on this particular curve, right? So this curve, if at all you have to go in detail about it, the resources also provide the link to it. This curve is called the SEC P256K1 curve, right? So it has all the details and it refers and it's used in the Bitcoin's public key cryptography, right? So more details are also shared on this particular wiki page as well. And all this, the equation of the same, right? The equation that we were talking about, pi square equal to x cube plus 3. All the details are also mentioned here. And there are other resources that are provided in the lecture as well, right? So we've discussed about it in the previous sessions. So this is not like a third party. It is something that is behind the signing and verification of the algorithms that use public key cryptography. Yeah, I hope that answers your queries. Yes. Thank you so much, sir. Great. So these are a few points that we have understood in our previous hackathons. Now, coming back to our current session, the immediate previous hackathon. So we have discussed here more about the elliptic curve, and we've understood that all the signing in whenever you pass in a hash of an agreement to the signing algorithm, it is going to generate a few components, which is known as S and R, right? So all of that is there. This is the logic of it. Everything is available online, but it is a very solid and algorithm, and it is very difficult to forge. Right? So this is something that is behind the digital signatures, and what it uses is the elliptic curve. So the elliptic curve digital signature algorithm is something that is part of the Bitcoin system, right? So in our previous session also, we've understood the same points. The signing and verification ensures the authenticity of the transaction. And we've also taken one particular example. We have taken a particular example of how the Bitcoin wallet address is generated, right? Just to quickly understand, what we have done is the public key of a particular individual or a particular user is a 512-bit string, and that is double hashed, meaning first it is processed with the SHA-256, right? So we have also seen that in our previous lectures. The resources of the same are also available on Teachable. Okay, so let me share where it is available. Yeah, so you can come here and see this. Yeah, so one of the resources that we are talking about is P256K1 curve, and the octal, the binary conversion, all of these are mentioned. So let me share the resource here on chat as well. Okay. Yeah. Great. So now if you see, one of the resources that we have discussed previously is this particular page. So what happens is whenever you have the public key, which is going to identify you on the whole, identify your wallet alone, that is used as an input to the SHA-256 algorithm. So we have seen, for example, if you're going to give the 512-bit string as an input here, I'm going to give a random string. So let's just say I'm going to give an input, let's say here, some say my name, and there is a 256 string that gets input. So here I'm going, giving you a hypothetical case. Here, instead of whatever I have written, here you will be having the 512-bit public key, right? So then that key is going to identify your wallet or your user, and this input is going to be used and sent into as an this output is sent as an input in the RIP EMD 160 algorithm. So when you give that as an input and click on encode, so this happens within the wallet ID generation only. So then you will have a shorter string that gets generated, right? So earlier, whatever 512-bit was there, it got compressed into a 256-bit string, which is something one-way function only. You'll not be able to go back and understand because you have the hash. You'll not be able to generate what was the public key. Now, after that, to also have better security and more, compressed output, you again hash it with another hashing function called RIP EMD 160, and you pass that particular output from the SHA-256 comes as an input to RIP EMD, and you'll be having a 160-bit string. Right? So we have discussed that here. Even professor explains that in his lectures. The public key goes first, gets hashed using the SHA-256. The 256-bit now goes as an input to RIP EMD 160, and then this 160-bit output comes, right? So this is like a 20 bytes of string, because now 160 bits, 8 bits make 1 byte. So 160 by 8 gives you 20 bytes, right? So now you have a 20 bytes output, which is having within itself the public key in that, right? So that particular input, it is already having. Now, instead of directly giving this as your wallet address, what we are going to do here is whenever a wallet ID is getting generated, it also has something called checksum along with this 160 bytes. Now this 160 bytes has your public key, but what happens is when you are entering any particular wallet address, sometimes what happens is there could be an error in one particular character because it's a long character, and if there's any error happening, what happens is the amount that you are trying to send gets lost, right? So there's no other person having that the ID that you have entered, and you'll not be able to reverse it back, right? So for that reason, there is something called checksum, and we use that checksum. Now what happens, let's try to understand. So now this checksum is a 4-byte string. So you also understand, we also have seen a resource for the same, right? So let me share it diagrammatically to make it easy. Great, let me share my screen. Now you can see that this particular how this works is you have your 160-bit string which consists your public key, and there is a checksum also. So let's see an example of the same. So your 160-bit string, which is nothing but 20 bytes, is accompanied with a checksum, right? This also gets generated within the algorithm only. So whenever there is change in the address, let's just say if the address changes, I'm giving some other number, the checksum changes, right? So what happens is when you are sending the wallet address, it always consists of a checksum. So if the initial portion, because this is sent as a 24 byte string when it is sent forward, so it consists of the checksum along with the RIPMD 160 output that got generated. So whenever there is some change in the first portion where the data is there, like for example, there is 7 here, it will not match the checksum. So now you can see that the checksum is above related to this particular data, but when some tampering happened, when some change happened here, this data before the 20 byte data is not matching the checksum, and there will be an error. And for that is how you would be able to protect yourself of any manual error that could happen, right? So whenever a wallet address is generated, it also has a checksum in it. Yeah, so whenever there is so Vasu sir, I've understood your question. If there's a mistake in the 160 bits, the checksum will also contain the error. So what is the checksum achieved? So now what I'm doing is like, for example, I am here trying to show you, for example, this is the checksum, this is the data which consists your public key, and related to that there is a checksum. Now if at all there is an error in this data, so now I'm going to change this 7 to 9. Okay, here you can see that it is not matching the checksum, and this particular thing changed into red. So what checksum is achieving is if there is any error happening in the initial portion of the data, it will not match here itself, and the error will be pointed out, right? So the point you are saying is when the data changes, the checksum also changes. So with every different public key, correct. So the mistake will happen in the public key, because that is where your that is where the hash of your public key is there. So the probability of mistake is there in the first portion, right? Checksum is only there to protect you if there's an error. I hope that is clear, sir. Right. So these links to these also will be there on your Teachable. So you'll be able to, yeah. Okay. So I hope, let me repeat that once again, sir. So once there is a 20 byte input that is coming here, there will be unique checksum that gets generated, right? So let us try another example. So now this particular input that is coming after the public key is first processed through the SHA-256, and after that it went into the RIPMD 160, and that output is this 160 bit, right? So if there was any error that happened in the public key here itself, the RIPMD, whatever is getting generated, will have an error. So for example, you have generated this and you want to send this whole ID, the whole text forward, right? I'm copying this and I'm sending it, let's just say I'm sending it to you over email, right? So when or maybe let's say I'm meeting you, or I'm giving it to you in physical, right? So whenever I'm giving it to you, if there is any error I've done here, right? So by mistake, instead of D, I have written B. Now what you are going to do, you're going to enter it to send some message. When you are going to enter it, send some Bitcoin and that particular portion, this will not match and you will not be able to go through, right? Correct. Yes, sir. The mistake, if it will be there in the RIPMD 20 bytes of data. So even to avoid all this, sir, what happens as we go forward is now the whatever output that is getting generated, the 20 bytes along with the 4 bytes, because till here we have not generated the wallet address. So now here whatever got generated is your data plus checksum, but this is not your wallet address. Now to have your wallet address, because what happens in this data is you can see that there are some characters, because this is like hexa. There is O, that is something that you can see, and there are a few other characters which could be ambiguous, right? So now this, if you're typing or sending it manually to someone, somebody might get confused if there is an I in this. Like if let's just say I'm entering, instead of this 6, I'm entering I. Okay. Okay, so when this is getting generated, so what is going to happen is there could be some confusing characters that come out, right? Like even you can get confused about 0 being O or small o or capital O, all those things, right? So that is where we do another process, which is converting this into a 52-bit code, right? So 52-bit base, right? So how do we do that is here. So now you can see that whatever input with the 20 bytes along with the 4 bytes got generated, we are going to convert it into base 58, right? So now when you have base 58, what happens is it will have 62 characters in it, which is the uppercase 26 alphabets, the lowercase 26 alphabets, and digits 0 to 9, right? So in here, you will be removing all the digits that are ambiguous, right? So there are 4 characters that are excluded out of this whole system, which is the uppercase O, then the number 0, the lower L, and the upper I, because the lower and the upper I may look similar, right? So after that, your final wallet address gets generated, right? So this removal of the symbols will reduce all the confusion. So let me show you one final reference which will clarify all of this for you. Great. Let me share my screen. Right. So now if you see the input that comes out of the checksum that is getting generated here, data and checksum, the combined input, the 24-byte input, is then converted into a base 58. And what this base 58 does is it has 58 digits, characters that it uses. It has, if you can see from hexadecimal, it does not have 0 in its characters. 0 is removed to remove the ambiguity. The capital I, the uppercase I is not there. The uppercase O is not there, and you can see that the lowercase L also is excluded, right? So you can give an input, whatever input that is coming, and convert it into a base 58. So let me show you an example. So if you are able to see my screen, yeah. So whatever output that got generated here, I'm going to pass this as an input to the operator here. So for example, if I'm going to give this as an input, you can see that the base 58 of the same would be a string like this. Now this will go ahead and become your wallet address. right? So this wallet address consists of your public key, which is double hashed. And after that, it is accompanied with a checksum and then converted into base 58. Yeah, so here you can see that here it will not be there. So the user says the lowercase o is there. I'm sure that you'll not be able to find it in the base 58. Small I is there, sir. Vasu sir, small I is there. The capital I is not there. You can see small I is there in the system. Small L is not there. Yeah. So this becomes your wallet address. So how the wallet address gets generated is it goes, the public key of yours becomes a hash, then it goes into your RIP MD160 hash, then accompanied with a checksum, and the whole input goes and gets converted into a base 58, and that becomes your wallet address. So normally we can always share the wallet address to other person, but what happens is, because we are in the study of it, we understood what goes behind the wallet address and how it is heavily secure, and what is the process behind the generation of it, right? So this is something that we have also seen in our previous session, right? So if this particular portion is clear, sir, how a wallet address is generated, and type C in the chat box. Thank you, Vasu sir. Thank you, Sujima. Great. So now we'll also try to understand. Yeah, thank you, Sharai. Thank you. Thank you so much. Now, previously, what we have done is we've gone on to the bitcoin.com, and there we have identified one of the specific block, which was the block 5 lakh, right? So in this particular block 5 lakh, so basically people who are watching it for the first time, this particular explorer will give you knowledge about what transactions happened on whole of the blockchain. You can even go to the block level and see what all transactions happen, right? So we understood a little about this in our previous session also. So I'm going to repeat that for everybody's benefit, right? So here on the whole blockchain, we are going to see one particular block, which is the 5 lakh block. This is something which is, this particular block was created in 2017, right? So it will have all the details about it. Now you can see that this was mined on December 19th, 2017. And now you can see that what was the total Bitcoin amount, the information about roughly 14,017 Bitcoin was available or was added onto this particular block, right? So there's an average transaction of each of the block, each of the transaction in that particular block has been mentioned, right? So we've understood in our previous session how to read the transactions in a block, right? So whenever you identify a block, it will have a few properties, a few details about it, like what is the input value, what is the output value, what is the fees that was sent to the miner, right? So you can even go to the Genesis block. Genesis block is nothing but the first blockchain first block on the blockchain, right? So I'm going to search for one. You can see that there's block 1 here. Now you can see that this particular block was mined on the January 9th of 2009, right? So it will have the details about the ownership of it, right? So this particular block does not have it has 0 Bitcoin were sent in this block, because this was, if you remember in our initial sessions, this block was used to send the message, a text message, which was related to the financial crisis. So it was not having any specific transactional output, right? So all the details like how much time it has been, and who was the miner. So the miner for the first block is not known, right? So now you can see a lot of details here. All of these details have some significance. We have discussed a few of these, right? Every block has a few transactions in it, right? So how does that work? We'll try to understand. Now, the transaction is the fundamental unit in cryptocurrency. Now, these transactions are loaded onto the block by the miners. Now, miners are people who are using their computational power of their devices or their time onto processing and validating new transactions that are getting added onto the blockchain, right? So for example, if you have sent some currency, some Bitcoin to some person, let's just say 0.03 to some person, a portion of that is going to as a transaction fee to the miner, the person who is going to validate it. And this is sometimes, many a times, maybe an agency or an exchange. It could be an automated process also, but there is some person who is validating it, right? So that person will get a portion of that particular transaction fee. And there are ways to even specify how much transaction fee you want to give. But only thing that we want to ensure is, if at all there's an urgency for you to send in that particular transaction, the incentive for the miner has to be larger, because all of the miners who are there who are validating this transaction get a block reward, which is the transaction fee. And if you have a very low transaction fee that is there, that is happening, your transactions might get delayed getting loaded onto the blockchain, right? So this is something that we'll also discuss. So transactions are responsible for making the whole system run. We have tried to understand the transactions also. So the user transfers some amount of cryptocurrency to another user. The output, there are two portions. We have even seen in the blockchain 5 lakh, there is output and input. So the output specify the amount and the address of the transfer, right? So for example, if I want to send to one person, say Rahul, I should know the wallet address of that particular person, and that should be specified in the during the transaction. Without that, it will not go. So the inputs that we are giving is the amount and the address for the transfer, right? So a single transaction may have several outputs and recipients also. We're going to see that also, right? Even in the 5 lakh block, we were able to see there were a lot of transactions, and each transaction has its own outputs and different recipients also, right? So we have seen one example in our previous session, which was this, where let's just say there is Tom, and he has 5 Bitcoin with himself, and he wanted to send 2 Bitcoin to Alice. And this is one transaction, but this transaction contains 2 outputs, right? So how we do transactions in a real world is, you have an input. Let's just say you have 5 rupees and you send 2 rupees. The balance left with you is 3 rupees, right? So in Bitcoin world, the transactions happen differently. So how does that happen? You send some portion, let's just say out of 5 Bitcoin, you send 2 Bitcoin to Alice. The balance is whatever is there. It does not remain as balance in you. It also gets converted as an output, but the address will be your own, right? Tom's own address, right? So 2 Bitcoin will go to Alice, and 3 Bitcoin is something which is called unspent transaction. So this is not spent, and this will be routed back to his own wallet, right? So these 2 outputs made this whole single transaction, right? So we have understood that each transaction can have multiple outputs. Now, this one output is to Alice, which is clear. The second output is to the address of Tom himself, right? So there could be multiple outputs like this. If at all you are trying to send some a particular Bitcoin to Alice, and let's say another person, say Carol, and let's just say you're sending out of 5, 2 to Alice, 1 to Carol, and the balance 2 Bitcoin is marked as an unspent transaction. So this is something that is not there in our real world. So that is where we'll try to understand it, right? So what is this unspent transaction output? Right, so UTXO, the unspent transaction output, because all these outputs that are getting generated here, out of this is this unspent transaction, right? So now this is generated on every transaction. Whenever you're trying to send any amount to any person, whatever is not spent is made as an output, but the wallet address for that will be your own, right? So this is called as an unspent transaction output. Now, the UTXO is the specification of the money available for transfer next time, like, whatever you want there, that will be specified for the money available for the transfer. So the whole network maintains a record of all unspent transactions, right? So there is something called the UTXO database, where all of this unspent transaction outputs are shared, are uploaded, like are getting recorded, right? So for example, we'll see we'll see the example and then come back to the slide. Now, if you see the same example in a detailed way, now this particular person, Tom, has 5 Bitcoin and he received it in 4 parts. Someone sent 2 Bitcoin, 1 Bitcoin, 1.5 Bitcoin, and 0.5 Bitcoin separately. So this is what the input was there, and that is where he had 5 Bitcoin in his wallet, right? So whenever he's trying to send, let's just say 2 Bitcoin to another person, the transaction will be created in this fashion. Whatever input that was there, which is equivalent to 2 Bitcoin, will be first unlocked, and then that is sent forward to the person. So then 2 Bitcoin is something that Tom wants to send, and that output is logged again here, and that is sent forward, right? So if we come back to this particular slide, now what is happening here is the whole Bitcoin is maintaining the database or the records of all unspent transaction. And in this, for example, you had 5 Bitcoin, and when you sent 2 Bitcoin, the 3 was there as unspent. And next time you send another 1 Bitcoin to other person. So this 3 Bitcoin, whatever was there unspent, this record will be, taken off the UTXO database, and a new UTXO gets recorded, which is of the unspent, the actual current unspent, which is 2 Bitcoin, right? So this keeps on updating. The UTXO keeps on updating based upon how much ever the transaction is happening on the whole network, right? So this is what we clarified in our previous sessions also. If there's any doubt in this particular portion, you can even ask us, right? So yes, so we have user, I'm not able to know the names, so we are going to also refer to Professor Pandurangan sir's transactions. We are going to in detail about what happens in the input and output in our coming hackathon, which is tomorrow. We are going to have it tomorrow, where we are going to discuss in detail about this, sir. I hope that is clear. So we're going to discuss about it. Any specific query you have? Yeah, okay, thanks. Any specific query you have, because I can see that you are putting the whole message that Professor Pandurangan sir has mentioned. If at all there's any specific question, you can ask us, sir. Yeah, so now UTXO is generated when a transaction is made and specifies the amount and the address of the recipient. Okay, A and B are the queries of the messaging checkbox. Okay, thanks, sir. We'll cover that in the upcoming hackathon. So now the UTXO serves as a record of the transaction and tells the network that there is some money with the sender and that is to be transferred to the recipient. The transaction can have several outputs with different amounts and addresses specified. The total sum of the outputs in the transaction must equal the amount of unspent transaction referred in the transaction, right? So now this is where the small, here we are not discussing the transaction fees portion of it. Here we are trying to understand only a person trying to send some amount to other person, and whatever remains is marked as unspent transaction output. But there is also a portion of fees out of this that is going to the miner also, right? So now we'll discuss more in detail about that, right? So the amount in the transaction must be specified in Satoshi. So we've also seen what is Satoshi, which is something 1 Bitcoin in Satoshi, right? So you can see that each Bitcoin is made up of 100 million Satoshis. You can even, this fees or whatever charge is there, even that has to be mentioned in Satoshis, right? So if at all we have seen the transaction here, the on the block 5 lakh, let's go to the R5 lakh block. So it will be mentioned in Satoshis. Yeah, so now you can see. If there's a question, you can go ahead and ask, sir, or else you can mute. Great, thanks. So now we're going into this particular block. It has multiple transactions. I'm going into one particular transaction. Yes. So now if we see this particular transaction, yeah, so you can see we have so the fee here is mentioned as 17. So basically the amount of Bitcoin that was sent in 2017 December 19 was 0.12 or 0.13 Bitcoin, and the fee for that was mentioned in Satoshis, right? So now you can see that the fees is a smaller portion of it, like on an amount, accounting to 3,000 USDs, the fees was $4, right? So over 3,006 USD, the transaction fees was $4. You can, that was specified in Satoshis, right? So you can even see that $1 in Satoshi also. So you'll be able to get that particular number, right? So here, let's say $4. You have many converters. At $4 is 17,723 Satoshi, which is something closer, right? 17,000 Satoshis. So this is mentioned, and portion of that goes to the miner also, right? And all of this is mentioned in Satoshis, especially the fees. The amount in the transaction must be specified in Satoshis, the lowest denomination of Bitcoin, right? So the transactions are indivisible because that is the core unit that runs the whole Bitcoin system. So that is the atomic part, portion of the whole, block, meaning that the specified amount cannot be split into smaller denominations for transfer, right? So when a transaction is made, the unspent transaction referred to becomes a spent transaction. Like for example, whenever, earlier there was 3 Bitcoin as unspent transaction, and once it is spent, once out of that 3 or 2 Bitcoin is spent, then the previous UTXO, the unspent transaction output, is disqualified from the networks and the new one gets generated. The spent transaction is removed from the UTXO and the new transaction becomes a new UTXO, right? So if UTXOs is clear, type C in the chat box. can see, yeah, okay. So what is Satoshi? So Sharayu asks, what is Satoshi? Now, thank you so much, Sujima. So Satoshi, like how we have 100 paisas making 1 rupee. Similarly, Satoshis, 100 million Satoshis make 1 Bitcoin. So it is the smallest unit of Bitcoin, because now even Bitcoin in value is so high that you'll not be able to always send 1 Bitcoin to someone, right? So it is, so you can send in Satoshis. You can mention the transactions in Satoshis. So Satoshis is the smallest unit of the Bitcoin. Yes. Correct. So yes, Vasu sir, in verification, no double spend has occurred. So while verifying only, the question of Vasu sir is, when a miner is verifying a transaction, no double spend has occurred. So if that is the question, so now you can see that in our initial lectures, we have understood double spend is completely rejected in the Bitcoin system. So whenever, because everything is every transaction is hashed and every hash is unique, right? So if a same transaction is again put back onto the block, it would have the hash, whatever is there, either it has to be manipulated, or same I mean, the previous transaction, what was there, has to be manipulated, and that will be easily understood by the blockchain. And because this is a public ledger, even if there is somebody trying to double spend it, somebody saying that I spent the same Bitcoin to 2 people, whenever somebody is trying to do that, because the public ledger has information that this person only had 1 Bitcoin, and there's no way that he can send the same Bitcoin to 2 people, it will get auto rejected, right? So no double spend. While verifying itself, the no double spend is definitely going to be satisfied. Thank you, Vasu sir, for the question. Yes, thank you, Sharaya. Now, so that is what we've understood. Now, each transaction, because now you see that transaction is the smallest unit, and what does this transaction have? What is the, how does it work? What is all included in the transaction? So whenever a transaction is recorded, we'll see how a transaction looks like also, right? Right. So let me go to our block file and show you. Here. Now we can see this particular block. We have in our file block, we can see that there are a lot of details in that. Out of that, we have identified 1 transaction. So in this, we have gone down, and there are a lot of transactions. There are roughly a huge number of transactions in this. Out of that, I'm just going to, because we've also understood that every block can hold data of 1 MB, right? So which means because based upon the transaction, if it's a smaller transaction, smaller bit stream gets uploaded. So every block will have different number of transactions that it can hold, right? So now this particular block has a lot of transactions. Let's just say 2,701 transactions are uploaded onto the block, meaning are verified while adding onto the block. And out of this 2,700 transactions, we are going to see the third transaction here, starting from 0, 0, 1, 2, 3. We are seeing the transaction, and in this particular transaction, you can see that the structure of the transaction is all. So these are all the properties that are there. Here, what is happening is all the detail here is being graphically represented for us. But when it is uploaded onto the blockchain, it is more of just like a transaction, single bit stream, right? So it is not saved as like position is 3, age is so and so much. Here, that information is made easy for people like us to understand. But you can see that particular transaction, the hash of that particular transaction ID is also there. So the hash is there, and more details about it, the hash ID and the all other input and output related details are uploaded onto the transaction, right? So what is in that particular transaction is this, right? So first there'll be a version, so which is something technical, we need not have to have an understanding. For example, now this person Tom wants to send 2 Bitcoin to Alice. Because he already has an input worth 2 Bitcoin, he only has to send one input that and one output, right? So the input counter will be 1, the output counter will be 1. The input is of 2 Bitcoin, the output is also of 2 Bitcoin, and this is what is included in the structure of the transaction. And there is a timestamp. Whenever the output has been logged, that timestamp is also part of the transaction itself, right? So what happens if Tom wants to send an odd number of, he does not want to send 2 Bitcoin, he wants to send, let's just say 2.6 Bitcoin. He does not have an input which is exactly 2.6 Bitcoin, because he received 2 Bitcoin separately and 0.5 Bitcoin separately. So now he wants to, if he wants to send 2.6, he'll have to club this particular 2 Bitcoin with this 1 Bitcoin, because this and this would only make 2.5, but he has to send 2.6. Now 2 plus 1, 2 inputs are logged, and the input that is coming, like it's like the supermarket cash counter, how much you have given a 500, what was the bill, and what has to be the output. It says if yesterday I've given a 500 rupees note and the bill was, let's say 250, the output, it says like you have to give 250 and so many notes and all, right? Similarly, the input here was 3, and the output that we want to log is 2.6, because that is what has to be sent, right? So the output counter, and what happens is the 0.4 Bitcoin, whatever is there, is sent as an unspent transaction or UTXO, and sent back to Tom himself, right? So in that particular output comes as a single output to Alice, right? So this is how the transactions are happening on the blockchain, and this is the structure that is there on the block. Each transaction is having this kind of a structure. So we've understood this, right? So we've understood about the Satoshis also. We've understood when we are transferring funds, multiple transactions, funds can be transferred using a single transaction or multiple transactions, and multiple transactions can be pulled together to transfer the required amount, right? So if you are sending in a bigger transaction, then it can go into multiple transactions, and that could be used in that particular block, right? If you are even sending more transactions that are not happening adjusting in the one single block of the 1 MB space, it will take a portion of the second block also, right? So the seamless transfer of funds can occur even if multiple people have paid to the same address, right? So that is possible. So the number of outputs Sharayu will be 1. So the output that gets generated here in this particular example, when the inputs are when he's trying to send 2.6, the inputs would be 2, but the output would be 1. Yeah. So Suju ma'am asks the Genesis blocks Bitcoins, the UTXO, how they've got generated, right? So because in terms then that particular block, the Genesis block, did not have a financial transaction, so it had only the message that was sent in. So even I would also have to look this up, Sujamam. I think let me also go ahead and do that. But the mining process, whenever more transactions were happening, let's say in general, when you use an exchange to convert your regular money into, we'll also cover this as we go forward. So when we are when you're converting your rupees into dollars or dollars into Bitcoin, so the transaction gets created and those get uploaded onto blocks, right? So when you're doing a new flow is coming into the network. Yeah. So why?
Okay, maybe we can explore it more.
Yes, 100%, madam. I will definitely.
Also, no transactions are initiated by the Genesis block because unknown, isn't it?
Correct. So basically, yeah. So if we go through our Genesis block, so let me show the slide. Okay.
Yeah, we can look at maybe the inputs of this.
So even there's more details about only the Genesis block also. I am going to share more insights. I'll also do a little more assessment of what happened in the Genesis block. But
yeah, maybe we can do it later also.
Yeah, we can do it later also. But there is one input that that is interesting. Yeah, so let me share the screen. Yeah, so if my screen is visible, yeah. So when this transaction, the first block on the first block that was there, the first transaction contained this message which says the times 0 the third. Come back with more detail, but there was only one message that was there. And I'll also come back more on that, the same thing. Thanks.
Okay.
Yes. Great. So yeah, so now Vasu sir, when 2.6 Bitcoin is being sent, the person, the Alice, will receive it as like a one input, right? And the 0.4, whatever is there, that comes as an output, the UTXO as another output back to the same person, Tom. It goes as single input to Alice. I hope that answers. Great. So let's continue. Thank you so much, ma'am. Thank you, Vasu sir. Yeah, so transactions can have multiple outputs, sir, right? So it is still part of the same transaction, but it has multiple outputs. Like so we have discussed here. This whole is a transaction. It has multiple outputs, right? So it will be consisted in the same transaction, but with multiple outputs. I think that should answer, sir. Correct. Okay. So the outputs would be 2. Yes, sir. Thanks for that. Now I get it. Yeah. So more questions means more thought for us, more understanding happening. So I'm really happy about it. And if there is anything that like Sujuma might also understand more about Genesis, because I know that we'll even talk about more about the Genesis block and how funds get transferred as we proceed forward also. But thanks for bringing it up.
Yeah, sure.
Yes. Correct. So now we have understood this. Then we'll try to understand more about mining as well. So a transaction specifies the value and the address of the recipient. The public key of the recipient is specified in the transaction. The world will know the recipient by the public key. right? Which could be the wallet address of that particular person, right? So what role the signatures play in these transactions? So the recipient uses their secret key to sign the transaction. So this is done by the wallet. He doesn't have to do anything. If he's using his own wallet, means that he authenticated and logged in using his own ID, password, or key. So the recipient uses their secret key to sign the transaction. The signature ensures that world knows who is using the money, both sending and receiving, because we have seen the transaction, the input and output, the person who is sending, the person who is receiving, and the person who, the miner, the idea of that, all of that is there on the blockchain. So the signature is a physical part of the transaction that proves ownership, right? So that is also part of the transaction. So this is happening from your wallet, and so you're not trying to do something separately, try to use a signature algorithm or something, but when you're using a wallet, it automatically happens. So the signature is the digital signature that verifies the ownership of the funds in the transaction. Now you can see that all of that previous learning that we had regarding signature comes handy here. To sign the transaction, the owner will use their secret key to prove that they have control over the funds. The signature is included as part of the transaction and is broadcasted to the network, right? So when the transaction is happening, that that the signature is there, but when somebody has to verify, they can verify it using the verification algorithms, right? So it does not mean that signature itself is broadcasted. It is hashed, and the transaction verification, the signature includes the secret key, but it is not the secret key, right? So that's something that we have to keep in mind, right? So utilizing UTXO in context of a cryptocurrency transaction, and unspent transaction output represents the current state of ownership for a specific amount of funds. When a transaction is made, the UTXO is spent and the funds are transferred to a new UTXO, right? Unspent becomes spent and a new unspent transaction output gets created. So these are some points that are emphasizing or strengthening the points that we've discussed. So transaction fees. So now every transaction has a transaction fees. The miner receives the transaction fees because he's helping us process and validate the transaction, right? And the miner's address is not specified by the user because he himself is not aware who's going to verify that particular transaction. But when the verification happens, automatically that address gets mapped by the wallet address, by the wallet or the exchange, and you will have it in your details, like post transaction. All the details will be there on the block. You'll be able to identify the miner's address also. Even anybody else can also identify it, right? So how do we calculate transaction fees is whatever input was there and whatever output was there. In some cases, the unspent transaction output, whatever, if at all you have not specified the transaction fees of that particular person, whatever is unspent could go to the miner. So that is the reason what you can do is you can specify the unspent transaction output. For example, you are sending out of your 5 Bitcoin, 2 Bitcoin to Alice. You can say, send me back 2.9 instead of 3, which means whatever rest remains, the 0.1 goes as a transaction fee to the miner. So when you say instead of the output, if you specify, there's a way to specify, we'll also discuss about it. When you specify that instead of the unspent being 3, keep it only 2.9, you are letting the block know that 0.1 is going to be the transaction fees. Let that go to the miner, right? So this is where people can set how much unspent that they want to get back, which indirectly specifies how much transaction fees that they want the miner to get. Based upon that incentive, their transactions get processed faster or slower. right? So we'll also see that. So the importance of transaction fees. So miners need incentive because it's more peer-to-peer and there's no single authority maintaining it. So the miners need incentive for maintaining and verifying transactions. So the transaction fee is a way of paying the miner for their work. So if transaction fee is low, the miners may not include it in the block, right? So include it meaning there could be a delay in your transaction getting processed, right? So how transaction fees are calculated? So for example, the transaction fee is calculated as the difference between input and output. For example, you are sending, I'm going to iterate the same example. If you are sending out of your 5 unspent, sending 2 Bitcoin to a person, and you can specify that you want 2.9 to be back, and whatever remains, input minus output is going to be the transaction fee for the miner. In case you're not specifying, some cases the transaction fee is default set. If you are using any specific exchange, they have a default transaction fee set that gets debited, whatever is unspent comes back to you. So the appropriate level of transaction fee is needed for quick approval. You cannot wait every time to see what will be the transaction fee for this. So many of the exchanges have set transaction fees. So you do not have to worry about how much this particular transaction is going to be charged for, right? So you'll have a clear idea of the same. Yes. So now factors affecting the transaction fees. Now transaction fee depends upon the size of the transaction, right? So miner prioritizes the transaction with high transaction fees. So whenever a bigger transaction is happening, like let's just 3,000 USD transaction that we have seen, there's a bigger transaction happening and he's going to get higher transaction fee, let's say $4, and he's going to prioritize that over another transaction where he's going to get $0.5, right? So that the size of the transaction is also going to be affecting. Like basically happens in banks also. Like when a customer, there's a priority line where they do a huge transaction, they are prioritized over that. So something similar is happening here. So the low transaction fee may result in a delayed approval. That is something that is there. So the incentive of miners, something we have already discussed. So the block incentive brings money into the system. So transaction fee and the block incentive are added to the miner's reward. Miner receives the reward when a new block is created. Whenever a new block is getting created, he's getting the reward. So a repeat of the same points. And now let's try to understand a little bit more about, yeah. So when we are trying to determine the appropriate transaction fee, the transaction fees is not on the value of the transaction. For example, let's say you're doing a transaction worth 0.5 Bitcoin. The transaction value does not define the transaction fees, because it is the size of the transaction that matters, because a new block has to be created. So the block size is something that is helpful in determining the appropriate transaction fee. So how many blocks you are consuming? Is it portion of the block? Is it more blocks? Based upon that, and the transaction fee gets calculated. Many places it is set, right? So the block size limitation in blockchain means that a block cannot have more than 1 MB of data. So the number of transactions a block can contain depends upon size of each transaction. So miners will be prioritizing wherever they have a higher incentive, right? So this is something that we have concluded previously. Now that we have revised it, we have a stronger understanding of the same concepts, right? So now if we try to go a little bit deeper, we'll just take another 5 to 10 minutes to conclude this as well. So now if you want to understand the Bitcoin block, right? So we previously understood the overview of the current state of the whole blockchain. All of it can be, all of the blocks can be explored on the Bitcoin Explorer. we have understood how to find a specific block on the Bitcoin Explorer, and we have seen how the details are presented, right? So though that is not how they are stored, when a Bitcoin is being stored, it is stored in bitstring, but these are platforms that are making it graphically attractive for us, right? So we have understood the block 5 lakh. It could be any other block also. You can see Genesis, you can see block 6,000, 5,000. So we have seen the whole picture of the block 5 lakh. So it's 5 lakh. So the explanation, we've understood how to see blockchain explorer and understand each details, the date of creation, who mined it, who got it, all those details also we have seen. We also seen there what is the block reward and the transaction fees. So we have understood the block reward is basically the incentive that the reward that the miner is going to get, which is going to be the transaction fee for different transactions, right? So we also understood how transaction fees are added to the block reward, and we understood how block reward is now. This is one point that we need to understand now. So now this block reward is something that is going to is decreasing. So for example, early days, we'll also be covering more of this as we proceed forward, but now it requires more incentive as we more computational power for creation of new blocks, and all of this is there. But the block reward, whatever is there, it will be marginally decreasing year over year or after a few years to control the inflation on the whole blockchain network, right? So this is a deeper concept. We'll also be understanding more about it, but the block reward is set to decrease to control inflation that could be there in the whole blockchain network, right? So we also understand like in the whole transaction in the block, this is on the block explorer only. There are many platforms. We have seen bitcoin.com, you can Bitcoin Explorer, you can even see it in the Coinbase is another platform for that. So in that we have seen each transaction, we have seen how new money generated. So whenever mining is happening, so that is how new money is getting into the system or going to the miner. So that is all something that we'll also be discussing as we proceed forward, right? So, and because all of these transactions are happening through the transaction IDs and wallet IDs, the anonymity of that particular user is completely maintained, right? So no other place, unless the miner specifies like this is their pseudonym or name, until then we'll not be able to know what or who is behind it. We'll only see that there's a transaction ID, right? So that is what the anonymity is about. And even if they specify a name also, we'll not be able to trace back where and what unless we have more information about it, right? So we have seen the contents of the block 5 lakh. What is the transaction volume? We have seen that there are 2,701 transactions in that. And we've understood total how many total bitcoins transacted. We understood that. We understood what was the fee that was sent as a reward to the miner, and we have examined the transaction also. I'd also request you to go forward and do it, which will also be helpful in proceeding forward and going ahead to do your labs as well. Yes. So how to access the content of the transaction also we have understood. The transaction ID also, we have seen what is behind the structure of the transaction ID and how to access the transaction ID from the blockchain explorer. The size of the transaction also we have understood. The size of the block is fixed. The size of the transaction could differ based upon the the transaction itself, right? So inputs and outputs in transaction also we have understood. the, basically what is input, what is output, including the unspent transaction output, right? So overview of how the inputs are referenced in a transaction, we have seen that. Let's also see, we'll also be seeing more in our upcoming session, where we'll see our inputs and outputs in detail, right? So let me give you a small glimpse here. Now, in our upcoming session, we'll see it clearly, but if you see, there are more outputs and inputs that are specified within, right? Here the input ID and the output, what is this PK script, what is the SIG script. We'll also be trying to understand all of these, right? So here we are trying to say how the inputs and outputs are calculated. We have had the overview of it. We'll go in detail about more in what is behind the inputs and outputs, right? So there is one portion that will conclude our session, which is serialization. So now serialization is basically nothing but how a raw transaction looks like, right? So how it is transmitted and verified and stored, right? So all of the data here, you have the graphical view that we are trying to understand is mentioned here, but all of the data that is there actually on the Bitcoin is more into bit strings or a serialized format, right? So these are all the points that we have discussed till now, and in our upcoming session, we'll see more about input and output. And one of the questions from our members related to input and output, we'll also be answering that, which was related to transaction verification, which we'll take up in our upcoming sessions. So if you were able to comprehend most of the session in our previous and today's hackathon, if everything is clear, type C in the chat box. And if there's anything else that you feel that we have missed, or you feel that you have gone through the Professor Pandurangan's lectures, if there's any query coming up, you can also bring it up here. If it is something that we can take it up immediately, we'll take up, or we'll see how they can be answered. Thank you, Suju ma'am. People who are watching us on our social channels, you can use the chat. We have a way to yeah, thank you, Sharai. So we'll be able to see your chats as well. Thank you, Sushmita. Thanks, Vijay. Thank you so much, everyone. This concludes the most of the module 4. Thanks, thanks, Suju ma'am. Suju ma'am says thanks to everyone. Like always, thank you so much. So we'll see more of these in our upcoming session. Thank you, everyone. Yes, this will be uploaded in the inner circle and along with the presentations. Yes, thank you so much.